Welcome to Modern Retrogramming with Plasma. This is episode 5, Data Access Methods. Plasma can only access bytes or words, but there are many ways to calculate the addresses. Single dimension arrays are things we've already seen, and they are indexed off of a base address. There are type specifiers that will override how memory is accessed. The dot is the byte type specifier. The colon is the word type specifier. Note that the colon is actually twice the period. It's one period on top of the other. So if we go back to one of our array examples, we'll just quickly show that we can access one of the elements of the array. Here we'll just call them pix, and referencing the second value in the array. Remember, arrays are zero based. Now, the array was defined as a byte array, so if we put the type specifier of dot in there, it's synonymous, it doesn't change anything. However, if we use a colon, we will now treat this array as a word array. So let's see what we get when we print that value out. And I printed it out as a hex value to make it a little easier to see the difference in the way it was accessed. Now you notice we see 0403. And you can see that it actually is the second word in the array, if it were a word array. Now let's see how we can treat memory as a data structure. Here we're going to create a hypothetical image data structure. It's going to have a width and a height, and then the pixels that follow it. So if we want to access the pixel data, we can do a constant offset with a byte type specifier. And you see we still read that second pixel in the pixel array. But using hard-coded numbers as offsets is a little cumbersome. First, let's go back to our integer representation of our print. Let's use constants to help identify the elements in our data structure. Here we're creating offsets into our data structure where we can access the elements of our data structure. So we can replace that hard-coded 4 with now pixels. This makes a little more sense. We are now obviously accessing the pixels in the image. Once again, when we print it out, we'll see that we're getting the value 2, which is the second pixel in the array. Now, trying to create offsets this way is very cumbersome. So Plasma allows you to create a structure definition, which is fundamentally the exact same thing, but it calculates the offsets for you. So you just tell it what types you have in your data structure, and it will calculate and add as constants the different elements. So it's all exactly the same to Plasma in this case, and when we compile it, it runs just like it did. I use a T_image for the structure type, just sort of a definition that T_image actually will then be the size of the structure. Now, if you've never worked with pointers before, welcome to the rest of your life. Pointers are one of the most powerful programming constructs, but also can be the most infuriating. In Plasma, pointers are just 16-bit values that can point to anywhere in memory. So a pointer variable contains an address of another variable, hopefully. And that's the thing about pointers. The slightest programming error can thus point to anything, including hardware addresses, screen memory, stack space, even code memory. As I've said before, with great power comes great responsibility. So Plasma doesn't know if a variable is a pointer or not. You just have to use a variable with different pointer operators to treat it as such. So here we're now using a pointer to point to our pixel data. You can see that we're pointing to the first pixel in the pixel array. So that little @ sign is telling us to get the address of the variables we're looking for. Now here again, we can use the caret, the upper caret, as our byte pointer and the asterisk as our word pointer. Just like the dot and the colon reference bytes and words, so do the caret and the asterisk for pointers. Now, why would you want to use pointers? Well, with pointers, once they're set to something, you can manipulate them with pointer arithmetic. In this case, we can first point to our array of pixels, but then by simply incrementing the pointer, we can point to the next pixel in the array. So that's a very powerful concept when we go to accessing large amounts of data. And now you can see we have the first 2 pixels that we can reference simply by incrementing the pointer. Now, we can actually add more than just one. We can actually add the width of our image to move our pointer to the next row of pixels, all with one operation. The image width will move our pointer from one row directly to the next row. So we see 1 and 5. 5, given that our image is 4 pixels wide and 2 pixels high, would be the first pixel on the second row of pixels. Now we have more operators. We have the pointer to a word operator, which is a equals greater than, and a pointer to a byte, which is a dash greater than. They look like arrows, if you kind of think of them that way, with the equals being kind of a thicker arrow than the byte pointer to a byte. These allow us to reference structure elements from a pointer. So here, with our image pointer pointing to the address of an image, we can reference the width of it, which is a word, with the equals greater than, that thick pointer, and then we can get access to the pixels array, which are bytes, with just the dash greater than, the thin pointer. Passing pointers around is much more efficient than large amounts of data. If you have a data structure that's more than a couple bytes, then a pointer is usually your best bet. And here we saw here's 4, which is the width, and 2 is that first or the second pixel. Remember, the pixels are still 0 based. All right, so we've covered quite a bit. We have one more big concept to understand, and that's multi-dimension arrays. So let's clear all this up. Plasma, as we've seen earlier, can use single dimension arrays, but with multiple dimension arrays, they can be implemented a couple of ways. Some computer languages treat the array as one big monolithic block, an index into by multiplying the dimension elements by its dimension size to calculate the effective address. Others, Plasma included, treat them as arrays of arrays, meaning all dimensions except the last are treated as pointers to other arrays. There are benefits to both approaches, but using arrays of arrays allows Plasma to create efficient methods of accessing difficult memory, such as the nonlinear mapping of Apple's screen. However, defining multiple dimension arrays is quite cumbersome, and Plasma doesn't offer much help here. So although Plasma doesn't implement it natively, it's quite possible to create a monolithic array block and write the equation to implement the effective address calculation yourself. So here, if we create a two-dimensional array of 4 wide and 2 tall, 2 high, we can create our own equation by multiplying our y variable by the dimension of the x. So that's something you need to take note of. You're multiplying that second dimension by the actual size of the first dimension. And here again, you see we got 5, which is the first element in the second row. So x is 0 and y is 1. Now, let's go look at how Plasma does two-dimensional arrays. I'm copying some code in from the console.io library, which has an array of the screen row address values. The paste is a little odd. It put the words on a different line for some reason, so we'll just clean that up real quick. And then I'll show you how we access this as a two-dimensional array so we can get to character positions on our screen just as you would expect them to be laid out by X and Y. So first we have to use the type specifier for a byte. When using multiple dimension arrays, you have to use the type specifier if you're accessing bytes. It's always good to use a type specifier just so it's clear which kind of data you're accessing. Now you'll know when we run this, you'll see a flashing A, one line down on the first character position. Why is that A flashing? Well, if you've ever dealt with the Apple screen before, it actually uses what's called high ASCII. So the values to the screen need the high bit set. If you don't have it bit set, it will use the flashing or inverse attributes. So it makes it easier to see in this demo, so I left it that way. Now we can also combine some of these concepts. Here we're using another pointer to point to a row in the text screen array, the fourth row down. Remember, zero based. And we're using an x position of 5, so that will be the 6th position in the screen. And we can have our row pointer point to an array. So we're sort of breaking down our two-dimensional array. And here you'll then see where the A gets printed out. See if you can figure out where it'll show up. 1, 2, 3, 4 down. 1, 2, 3, 4, 5, 6 over. Perfect. Hope you enjoyed it. Please check out the GitHub website. Thanks for watching.